We've got a lot to do today. Anyway, anybody look up the average hole in a plastic bag?
I don't even any
There's no service inside this room.
There's no service there? Nobody has any service? Well,
There's no service on my.
I do.
We'll look that up, and it's like a half a micron. Anyway, it's very small, but there are holes in the bag. You know, a plastic bag. If you've ever gone around and picked up dog poop, and even though you seal the bag, the odor is overwhelming because the chemical that is causing that smell is effusing out of the holes in the bag. And it's not just one hole, it's many holes. So everything has holes in it. I mean, it's an odd thing that's not going to have holes in it. So even plastic bags, they have holes in it. So, yes?
How come if you have like a plastic bag and then you like seal it and there's air inside, it doesn't like leave the bag?
Because the rate of effusion is slow. Don't get me wrong, it's not fast. It doesn't come out very, very quickly. And the holes are very small. But the chemical, there are holes nevertheless. And it doesn't, air is odorless by and large. It's just nothing, It's the material that's in air that causes odor. But there are things that cause odors that come out of the bags, and you don't need a lot of them to smell them. Right? But even bags have small holes in them. Okay? So, what were you going to say, Enzo?
Oh, nothing. I had a question for
Okay. So effusion is the rate it has to do with the speed in which molecules are moving out through an aperture. And in the first part, I talked about, well, what is the size of the aperture? So look at review number 1 for that, because we talked about that at length. Okay, so Graham's law of effusion, we talked about it already. We talked about it in review 1. We talked about it here. The equation, we talked about. Anyone else? Yes? The heavier the gas, generally it goes more slowly than a lighter gas. Okay. What else? Combined gas law we talked about. What is combined gas law used for?
When
you have a gas, go.
And you don't have any of the constants, any of the pressure, volume, or temperature are constant.
Yes, when you have a gas and you're looking at pressure, volume, and temperature, and all three are changing, correct? That is going to be, you're going to use the combined gas laws. Now, can I use the combined gas law to measure the number of moles that is in a gas? No, I can't.
Because it's only to determine the pressure, the temperature, and the volume if you know the moles.
If you know the moles. You don't really need to know the moles, do you?
You need to know the amount of the constant.
No.
No, that's for the ideal gas law.
That's the ideal gas law. For the ideal gas law is essentially used for what? Or when is the ideal gas law used?
To find the energy.
You guys are not on today. You guys were more on last week when we were doing the review for the change in state tests. Yes. Using moles, what gas law equation do you use?
PV over Tn.
What is it?
PV over Tn.
No.
That's
PV. How do you generally write the ideal gas law?
PV.
PV equals nRT. So PV equals nRT. And when are you using that equation?
You want to know the amount of...
When you have moles, when moles are involved. Look at this. This is the combined gas law problem. Okay? Nothing's constant. Yes? They're changing. Yes? For instance, I have 4 liters of a gas at 2 atmospheres and 373 Kelvin. Are you okay with that?
Yeah.
Okay. How many liters of gas do I have? Okay. Pablo, could you not do that? Okay. Let me just check to see if it moved. Repeat it.
It did.
Okay, I can see that. Okay. All right. All right. Okay, good. We're back. Okay. Well, how many liters did I say?
4.
4 liters, right? 4 liters, 2 atmospheres, and 373 Kelvin, correct? Now, I want to know the volume at STP. How would you do that? Do it right now. Come on. Do it right now.
How many kelvins?
373 Kelvin. So it was 2 atmospheres. It was 4 liters. It was 373 Kelvin. And P2 is what? It's all standard, right? So P2 would be what?
Would be 273 Kelvin.
What would it be?
1.373 PA.
So, okay, so P2 would be
101 kilopascals.
101.3 kilopascals, right? And then V2 is going to be, we don't know, and T2 is going to be 273 Kelvin. So plug in and calculate it. What do we got? So it's going to be plugging in, we have 2, I'm going to leave off the unit labels, okay? Because we have atmospheres. Oh, this can't be like this, can it? So we have to change that to what?
1.
1 atmosphere, yeah. So it's going to be 2, V is 4, 373 equals 1 over
It's 5.
273. So what is it going to be?
5.85.
So I'm going to reduce the pressure. I'm going to reduce the temperature. So what do we got? We have 2 times 4 times 273 divided by 373 divided by 1 equals what?
5.855.
5?
Yeah, 5.855.
So 5.9, is that all right?
Yeah.
Okay? So, but do you know, well, you could, but are moles in the equation?
No.
No, they're not in the equation. If I was going to use a gas equation that involves moles, what equation would I use?
Yes.
The ideal gas equation. That looks at moles. It doesn't look at multiple conditions, it looks at one set of conditions. Where this looks at multiple conditions, this is one set of conditions. Clear? Enough said? Who was doing ideal gas? Anybody? How are we doing? Anything you want to add to that? No? You all right? Gay-Lussac's law we did. Combined gas law. What's the constant? What is that? What is ideal gas law constant?
It's the
8.31.
yeah.
Right, but you've got to make sure what units you have. In other words, R equals PV over NT. So if pressure, if you want it in kilopascals, liters, moles, and Kelvin, you have to calculate it as such. If you want it in atmospheres, milliliters, moles, and Kelvin. You have to calculate it as such. What we do, we have it as 8.1, 8 point what?
301.
8.31, but ours is what? Ours is kilopascals.
Times liters.
What is it?
Times liters, I think.
Liters
Yeah.
divided by mole
Kelvin.
Kelvin. You get it? Enzo, you all right over there? Everything's fine? Excellent. You get it or no? We're done.
Yeah.
That was part 3. We've got to go to lunch. You need nutrition. Good luck on the test, and we're off.